Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it.
This is section 5.5, which is on multiple angle, and product of sum formulas. And that's supposed to say formulas. Let's try that again. Formulas. There we go. All right. So first, let's talk about the double angle formulas. All right. And those are the following. We have sine of 2u is equal to 2 sine u cosine u. Cosine of 2u is equal to cosine square of u minus sine square of u. It's also equal to 2 cosine square of u minus 1, and it's also equal to 1 minus 2 sine square of u. And lastly, we've got tangent of 2u. In here, this is equal to 2 tan u over 1 minus tan square of u. All right, so these are all the double angle formulas. I'm going to prove here the second one here, cosine. So here's the proof for that. So proof for cosine of 2u being equal to cosine square of u minus sine square of u. All right, so here's what we're going to do. First, we're going to say that cosine of 2u is equal to cosine of u plus u. And then from the last section, we know that when we have the sum of two angles like this instead of cosine, this can be written as cosine, cosine, sine, sine. So it's cosine of the first times cosine of the second minus, right, the plus becomes a minus, sine of the first angle times sine of the second angle. All right, and in here I'll just remind you exactly what I'm talking about. If I've got cosine of u plus v, this is cosine of u times cosine of v minus sine of u times sine v. All right, it just happens to be that we have u and u, so all of these become u's. At that point, this right here becomes simply cosine square of u minus sine square of u, as we already had, as we already wanted to prove. All right, so there we go. That's the proof of that. Now, if I were to replace here cosine squared, now I know that cosine squared is the same as 1 minus sine squared. So what I can say here is that this statement really becomes 1 minus sine squared minus sine squared, giving us 1 minus 2 sine squared of u. Similarly, I know that sine squared is 1 minus cosine squared, so I can really write this line as cosine squared of u minus 1 minus cosine squared of u. But then we have minus a negative cosine, so it's going to become really cosine squared of u minus 1 plus cosine squared of u, giving us that 2 cosine squared of u minus 1 is equal to that original expression. So that's how we have all of these ways to rewrite cosine of 2u. All right, so first we've got the sum being written this way, and then just replacing it with some Pythagorean identities. Let's do some examples. All right, so and by the way, the other two, for sine of 2u and tangent of 2u, they will be proven in a similar way. Rewrite 2u as u plus u, and then use the sum and difference formulas for sine or for tangent. Okay, so let's do an example of how this can be used. So, example A. Let's say I said solve the following equation, and I've got cosine of 2x plus cosine of x is equal to 0. All right. Well, what I can do here is I know that cosine of 2x can be written in several ways, right? Cosine squared minus sine squared, or 1 minus 2 sine squared, or 2 cosine squared minus 1. What we want to do here is we want to bring it down to just one type of function, all right? Since I already have this over here in terms of cosine, I'm going to use this version of the expansion for cosine of 2x. So I'm going to say this part right here becomes, well, 2 cosine squared of x minus 1, and then we still have that plus cosine of x being equal to 0. At that point, I'm going to say let u be equal to cosine of x. Then I can rewrite this line as 2u plus u minus 1 is equal to 0, right? All I did there was rewrite the order of this. So, excuse me, 2u squared. There we go. So I can write this as a quadratic. And we know how to factor these quadratics, right? I start with the AC method, 2 times negative 1. So 2 times negative 1 is negative 2. I need two numbers to multiply to negative 2 but add up to positive 1. Those will be 2 and negative 1. How convenient. So we have 2u squared plus 2u minus 1 is equal to 0. From the first two, I can take out a 2u. I'm left with a u plus 1. From the second two, I can take out a negative 1, and I'm left with a u plus 1 equals 0. At that point, I see that both of these have a u plus 1, so we can factor that. So I end up with 2u minus 1 times u plus 1 is equal to 0, giving us that either u is equal to 1/2 or u is equal to negative 1. But then we know the problem is not about u. It was about cosine x. So what we need to do here is say cosine of x is equal to 1/2 or cosine of x is equal to negative 1. And at that point, we go to the unit circle. This one's going to have two solutions. Within the unit circle, cosine is equal to 1/2 at pi over 3, but also at 5 pi over 3. And over here, cosine is equal to negative 1 at 3 pi over 2. Again, these are all from the unit circle. And sorry, that's not true. Cosine is equal to negative 1 at pi. I confused that for sine for a second, but it's okay. We fixed it. So we've got x is equal to pi for when cosine is equal to negative 1, pi over 3 or 5 pi over 3 for when cosine of x is equal to 1/2. But notice the instructions didn't say that I need to be within the unit circle. So I need to make sure that I add the period of cosine. So plus 2 pi n on every single one of these. And there we go. That is our final answer. Let's do another one, or another example of how to apply some of these double angle formulas. So that was example A. Example B. Let's say that I'm told that sine of theta is equal to 3/5, and I'm told that theta is between pi over 2 and pi. And I want to find sine of 2 theta, cosine of 2 theta, etc. All right, all 6 of them. So sine, cosine, tangent, secant, cosecant, and cotangent. So the very first thing I'm going to do here is I'm going to start by figuring out what triangle this is implying. All right, so I start by drawing my x and y axis, and I'm going to draw my triangle this way. I know that it's in the second quadrant because it's between pi over 2 and pi. So I'm going to say this is my triangle right there. All right. And where this angle right here, that's my reference angle theta. And I've got sine being 3/5. I know from SOHCAHTOA that sine is opposite over hypotenuse. So this is the opposite. That's the hypotenuse. That would tell me that the adjacent side is 4 because it's a 3, 4, 5 triangle, right? We recognize that. If we didn't recognize that, we could have used the Pythagorean theorem to solve for the other side. Now, the one thing that we need to keep in mind here, though, is that we're on the on the left half of the plane, right? Meaning that this value right here, the horizontal values, need to be negative. So this is really a negative 4. And at that point, well, we can figure out all of this because we know that sine of 2 theta is 2 sine theta cosine theta. So what can we do here? We can say this becomes 2 times sine opposite over hypotenuse. So 3/5 times cosine adjacent over hypotenuse, negative 4/5. Giving me here 2 times 3 is 6 times 4 is 24, but with a negative it's negative 24. And 5 times 5 is 25. So I get negative 24 over 25. Let's figure out cosine. Cosine of 2u, well, I'm going to write this as cosine squared minus sine squared, and we're working with theta, not u. Cosine of 2 theta is equal to cosine square of theta minus sine square of theta. And at that point, well, we already know what cosine was. Cosine was negative 4/5. So we have negative 4/5 squared minus sine squared, and here sine was 3/5. So I've got 3/5 squared. Giving us here, well, negative 4/5 squared is 16/25 minus 3/5 squared is 9/25, giving me an overall answer of 7/25, right? Because 16 minus 9 is 7. All right. Now, let's look at tangent. So tangent of 2 theta, well, we know the formula is 2 tan theta over 1 minus tan squared theta. And, well, what would tangent be? Opposite over adjacent, right? From SOHCAHTOA. Opposite over adjacent, so I have 2 times 3 over negative 4 over 1 minus negative 3/4 squared. 2 times 3 over negative 4, that's 3 over negative 2, right? The 2 and the 4 reduced to being a 2 on the bottom. And negative 3/4 squared is 9/16. I have 1 minus 9/16, but I can think of that 1 as 16 over 16. So I end up here with negative 3/2 over 16 minus 9 is 7, so 7/16. All right. And at that point we say, well, we've got a fraction being divided by another fraction, so that's the same thing as multiplying by the reciprocal of the second fraction. At that point we see that these reduce, and we have negative 3 times 8 is negative 24, and then 1 times 7 is 7. So we get negative 24 over 7. Notice that I could have done this a little bit differently for tangent of 2 theta, because I could have said that this right here is the same as saying sine of 2 theta over cosine of 2 theta. We already know what sine of 2 theta is, and that's a theta right there. Let's draw that better. Sine of 2 theta we found out to be negative 24 over 25, and cosine of 2 theta we found that to be 7 over 25. So then we have a fraction divided by another fraction. That's the same as saying multiplied by the reciprocal. At that point, the 25's cancel out, and we end up with negative 24/7, which we already knew. So that's sine, cosine, and tangent, each of them of 2 theta. Now let's figure out the other ones. Well, cosecant of 2 theta, well, that would just be the reciprocal of sine of 2 theta. So we're just going to take the reciprocal of this. So it's going to be negative 25 over 24. Secant of 2 theta would be the reciprocal of cosine. So it's going to be 25 over 7. And cotangent of 2 theta is going to be the reciprocal of tangent. So just negative 7 over 24. All right. And there you go. That's another way where we can use a double angle formula. All right. Let's look at a different one. Let's see. So example C. Rewrite cosine of 3x in terms of cosine of x. All right, so what is this question really saying? This question is saying this expression, cosine of 3x, we can use different identities to rewrite it. And we want to rewrite it in such a way that we end up with just cosine of x. It could be two different powers, or it can have different coefficients. But the point is that we just want x on the inside, and we just want cosine. We don't want any other trigonometric function. So how are we going to do that? Well, first we're going to start by writing cosine of 3x. And we know that 3 is the same as saying 2 plus 1, right? And at that point, well, look what I have here. I have cosine of u plus v, right? So we know how to deal with that because cosine is cosine, cosine, sine, sine. So I can say this is cosine of the first times cosine of the second minus sine of the first times sine of the second. At that point, well, we have a formula for cosine of 2x, right? Well, we have three different formulas for it, but I want one that only has cosine in it. And that one was 2 cosine squared of x minus 1. And I'll do that with brackets. So that's cosine of 2x is 2 cosine squared minus 1. And then we've got that times cosine x minus sine of 2x. Well, sine of 2x was 2 sine x cosine x. And we still have that times sine of x. So far, what do we really have here? If I distribute this cosine to each of these, I end up with 2 cosine cubed of x minus cosine of x minus, over here I have 2 times sine is sine squared. So I've got sine squared of x times cosine x. But remember that we want to think in terms of cosine only. So in here, this sine squared needs to be replaced. And sine squared, well, we can use a Pythagorean theorem, a Pythagorean identity, to rewrite it as 1 minus cosine squared. And then we have that times cosine x. At that point, well, we can distribute the negative 2, as well as the cosine, and we end up with, well, negative 2 cosine of x, minus the negative is a positive, so we have plus 2 cosine cubed of x. And again, what I did there was distribute this 2 and this cosine into that 1 to get this, and then distribute it to the second to get this. All right. So at that point, I see that we have some like terms that we can combine, and we have 2 plus 2. 2 plus 2 is 4, so I'm going to write this as 4 cosine cubed of x. And then in here, negative cosine minus 2 cosine, that's going to give me negative 3 cosine of x. And now we're done. All right, but again, the idea here is that we could rewrite cosine of 3x in terms of just cosine this way. All right, and you can apply that same idea in the same process for sine of 3x or tangent of 3x, right? So on and so forth. Now, let's look at another way to use these or other ways that these formulas can help us. Now, let's talk about the power reduction formulas. All right, and here they are. If I have sine squared of u, that's equal to 1 minus cosine of 2u over 2. Cosine squared of u is equal to 1 plus cosine of 2u over 2. And then tan squared of u is equal to 1 minus cosine of 2u over 1 plus cosine of 2u. All right, now, where do these come from? All right, well, let me remind you that we had from earlier that cosine of 2u was equal to 2 cosine, well, actually, let's start with the sine one. 1 minus 2 sine squared of u. If I solve for sine here, or for sine squared, well, I can subtract 1 from both sides. So cosine of 2u minus 1 is equal to negative 2 sine squared. Divide by negative 2, I end up with cosine of 2u minus 1 over negative 2 is equal to sine squared. bring this negative to the top, and I end up with 1 minus cosine of 2u over 2 is equal to sine squared. So there you go. That's the proof for this one. All right, that's where this power reduction formula comes from. For cosine squared, similar idea, but use the fact that cosine of 2u is 2 cosine squared minus 1. That would be for cosine squared. And then for tangent, we'll just put sine over cosine, right? Because tangent is sine over cosine. So we put sine squared over cosine squared. You put this stuff over this stuff. The 2's end up canceling out and reduces to this formula. So those are the power reduction formulas. Let's see how these could help. And this is one possibility. If I said rewrite tan to the fourth of x in terms of first powers of cosines of multiple angles. So in here, well, I'm starting with tan to the fourth, but I want my final answer to be just cosines. All right, I'm gonna rewrite tangent to just be cosines. Now, notice I said of multiple angles here, so, and they had to be first powers. So that's different than from the last example that we did over here, where we were allowed to have different powers, but we wanted to make sure that the inside was just x. So now we're doing the opposite, where the inside is allowed to be more than just x, but the exponents must all be 1 because it says first powers. So let's see how we can do this. Well, we start with tangent to the fourth. Now tangent to the fourth is the same thing as saying tan squared squared, right? Because squared is to the fourth. And now we know what tan squared is. Tan squared was 1 minus cosine of 2x over 1 plus cosine of 2x. And then all of this squared. Remember, here all I'm doing is replacing this inside. Now, let's see here. If we expand this, if I square this out, well, what does that really give me? This gives me here, well, let me do it in 2 steps. I'll write this as 1 minus cosine of 2x squared over 1 plus cosine of 2x squared. At that point, if I expand the top, I end up with 1 minus 2 cosine of 2x plus cosine squared of 2x. On the bottom, I end up with 1 plus 2 cosine of 2x plus cosine squared of 2x, right? But the problem with this now is that we wanted first powers. Look at that. Those exponents right there are not to the first power. That's squared. So we still need to rewrite this somehow, right? And what we're going to do here is, well, we know how to reduce the power of cosine squared. So I'm going to rewrite this now as this is equal to, well, actually, let me make more space down here. This is equal to 1 minus 2 cosine of 2x. That part's fine. But cosine squared, this is the same thing as saying 1 plus cosine. Hold on. Let's see here. Let me first remind you what the formula was. Cosine squared of theta is equal to 1 plus cosine of 2 theta over 2, right? That's what the formula was. But notice here, I've got a 2x instead of theta. So if I've got a 2x here, if theta is equal to 2x, then over here, when I've got 2 theta, that will be twice this, so that would be equal to 4x. So when I go and use the property here, I need to make sure that I account for that in the inside here, all right? So in here, I'm going to end up with 1 plus cosine of 4x over 2, all right? And again, that's because the formula here goes from theta to 2 theta. So if this inside here, if 2x is theta, then 2 theta would be 4x. Similarly, for the bottom, I end up with 1 plus cosine of 2x plus 1 plus cosine of 4x over 2. And at this point, we're almost done. The thing is, we've got fractions on top, fractions on bottom. We don't like that. So what I'm going to do here is I'm going to multiply by 1, where that 1 is the common denominator. In this case, the common denominator is just 2. So I'm using the common denominator to rewrite this as 2 over 2, or to rewrite 1 as 2 over 2, right? So what does that do for us? Well, distributing this 2 times 1 is 2, 2 times 2 is 4. So I'd have 2 minus 4 cosine of 2x, plus in here, that's just 1 plus cosine of 4x, right? Because this 2 will cancel out this 2 in that fraction. Similarly, I end up with 2 plus 4 cosine of 2x plus 1 plus cosine of 4x on the bottom by distributing this 2 to each of these terms. Lastly here, as my final answer, combining like terms, 2 plus 1 is 3, so we have 3 minus 4 cosine of 2x plus cosine of 4x. Similarly, on the bottom, I end up with 2 plus 1 is also 3, so 3 plus 4 cosine of 2x plus cosine of 4x. And that right there would be our final answer. All right. So that's one possible way to use the power reduction formulas. All right. There's also something called the half angle formulas. So let's look at those. So half angle formulas. And the half angle formulas are as follows. If I've got sine of u over 2, that's equal to plus or minus the square root of 1 minus cosine of u over 2. Cosine of u over 2 would be plus or minus the square root of 1 plus cosine of u over 2. And finally, tangent of u over 2 would be equal to either 1 minus cosine of u over sine, or sine of u over 1 plus cosine of u. All right. Now, one thing I do want to mention here is that for these two, the sign, in other words, we have plus or minus there. So whether it's plus or if it's minus, the sign depends on the quadrant of u over 2. So for example, if u over 2 falls in the second quadrant, then sine of u over 2 would have to be positive. If u over 2 falls, for example, in the third quadrant, then we'll be using the negative, right? So on and so forth for cosine. Now, where do these come from? Well, they come from these. All right, notice that they're not that different from these. So let's see how so. And in here, I guess I'll prove this one right here. But first, so here's the proof. And first, recall something. Well, recall from above that sine square of u, well, maybe I'll do it in terms of theta. Sine square of theta is equal to 1 minus cosine of 2 theta over 2, right? That was a formula from above. Now what I'm going to do here is I'm going to say let v, or maybe let u be equal to 2 theta. That implies that u over 2 is equal to theta, right? So how is that helpful? Well, what I can do now is I can rewrite this now as sine squared of u over 2, right, instead of theta, is equal to 1 minus cosine of, instead of 2 theta, I've got u, and that over 2. At that point, taking the square root of both sides here, I end up with sine of u over 2 is equal to plus or minus the square root of 1 minus cosine of u, and all of that over 2, as stated right there. All right, that's what we got. Now for tangent, it's pretty simple. I'll prove tangent as well, and I'll do this one in red, I guess. So tangent of u over 2. So let's do that one. So we've got tan of u over 2. Now we know that tangent is sine over cosine, so this would be sine of u over 2 over cosine of u over 2, right? Which from here is going to be a lot of information. So this is going to give us plus or minus the square root of 1 minus cosine of u over 2 over plus or minus the square root of 1 plus cosine of u over 2. At that point, well, for for the sake of simplicity, let's just take the positive versions of these. All right. Now, what we're gonna do here is we're gonna say we've got a square root on top and a square root on bottom. I can just write all of this to the 1/2, and we're gonna have the fraction of 1 minus cosine of u over 2 over 1 plus cosine of u over 2. And then we've got a fraction divided by a fraction. Well, in this case, those 2's are going to cancel out. So I end up with 1 minus cosine of u over 1 plus cosine of u. And all of this to the 1/2. And again, what I did here was if I had a over b divided by c over b, notice I'm using b twice because they both have the same denominator. That's going to be a over b times b over c, because dividing by a fraction is multiplying by the reciprocal. And those b's cancel out, leaving us with just a over c. So that's what I did here. All right. Now, let's continue with this over here. What we're going to want to do now is we're going to want to multiply it by 1. But the one that we're going to multiply by 1 is going to be very carefully chosen. So first, I'm going to rewrite this. I'm going to have 1 minus cosine of u over 1 plus cosine of u. And I'm going to multiply by 1 inside of the parentheses here, because multiplying by 1, it doesn't matter where you do it, it doesn't change anything. So that 1 is going to be, well, the conjugate of the denominator. So I have 1 minus cosine of u over 1 minus cosine of u. And when we do that, well, what does that give us? We end up with, on top, 1 minus cosine times 1 minus cosine is 1 minus cosine squared. And then at the bottom, 1 plus cosine times 1 minus cosine is 1 minus cosine squared of u, right? But then, at that point, well, we still have all of this raised to the 1/2. On top, I have 1 minus cosine of u squared. On the bottom, 1 minus cosine squared is the same thing as saying sine squared. And then if I take the square root of both the top and the bottom here, I end up with simply 1 minus cosine of u over sine of u, right? Because the square root of a squared just cancels out, square root of a squared just cancels out. So that's how we get this first one, 1 minus cosine over sine. 1 minus cosine over sine. Now, how do we turn that into the other one? Well, if I've got 1 minus cosine over sine, then I multiply this by 1, well, the conjugate of the numerator, 1 plus cosine over 1 plus cosine. Notice that the bottom, I just leave it as sine times 1 plus cosine. The top, I've got the product of conjugates. The product of conjugates is the difference of squares. And now I have 1 minus cosine squared on top, which is sine squared. And I have this over sine times 1 plus cosine of u. And at that point, sine squared over sine reduces, so that we end up with just sine on top. This one over here cancels out, right? This cancels that out. And we're still left with 1 plus cosine of u, which that was the second one of these. All right. All right. So what is a scenario where we can use something like this? Well, let's do this. Let's say I had find cosine of 7 pi over 12. All right. Now notice that 7 pi over 12 is not in the unit circle. All right. However, what we can say here is that 7 pi over 12 is the same thing as saying 7 pi over 6 divided by 2. And the thing is that 7 pi over 6 is in the unit circle. So let's see. Cosine of 7 pi over 12 would be equal to cosine of 7 pi over 6 divided by 2. All right. And why do I want that? Because now this is in terms of cosine of u over 2. Right? And, well, cosine of u over 2, we know that that's plus or minus the square root of 1 plus cosine of u, not 2u, 1 plus cosine of u, all of that over 2. And the plus or minus depended on the quadrant of that we were working in, of u over 2. Now, in here, 7 pi over 12. Well, if we think about 7 12, 7 12 is bigger than 1/2, but it's less than 1. Why do I care about that? Because this right here tells me that we're on the second quadrant. And in the second quadrant, cosine is negative. So what we're going to say here is that this is going to be the negative of the square root of 1 plus cosine of u over 2. And in here, what was u? U was just simply 7 pi over 6, right? Because 7 pi over 12 was u over 2. So 7 pi over 6 would just be u. So what we're going to get here is the negative of the square root of 1 plus cosine of 7 pi over 6, all of that over 2. And we know what cosine of 7 pi over 6 is because that's in the unit circle. So I have 1 plus cosine of 7 pi over 6 would be negative radical 3 over 2. And we have that all over 2. So simplifying this a little bit, we get the negative of the square root of, let's do this. If inside here, inside the square root, if I multiply by 2 over 2, what I end up with here is, well, 2 times 1 is 2. A positive times a negative is negative. 2 times a half just cancels out, so I end up with just radical 3 there. And on the bottom, 2 times 2 is 4. So I end up with the negative of the square root of 2 minus radical 3 over 4. But we know that the square root of a over b is just the square root of a over the square root of b. So applying that here, I'm going to end up with just simply negative square root of 2 minus radical 3 over the square root of 4 is 2. And there you go. That would be our final answer there. All right. And again, I was able to figure this out without knowing. 7 pi over 12 is not in the unit circle, right? But I know that 7 pi over 6 is. So that's what I did there. We were able to manipulate this to use the unit circle. It can be used in other ways too, though. So let's say that I said solve cosine squared of x being equal to sine squared of x over 2 on the unit circle. So from 0 to 2 pi. All right. And well, the way that I'm going to start this is, well, in here, let's look at sine squared of x over 2. Sine squared of x over 2 would be sine of x over 2 quantity squared. But sine of x over 2, we know that that's plus or minus the square root of 1 minus cosine of u. Well, not u, in this case it's x. 1 minus cosine of x over 2, and then that squared. Now, the interesting thing here is that we have a plus or minus. We don't normally like that. But the fact is that it's being squared. So whether we're working with the positive version squared or the negative version squared, either way, this right here is going to go away. And not only is this going away, but also the square root is going away because everything's being squared. So it's just 1 minus cosine of x over 2. So that's sine squared of x over 2. So that allows us to rewrite this equation here simply as cosine squared of x being equal to 1 minus cosine of x over 2. And that's a much simpler equation, right? In fact, if I multiply it by 2, I end up with 2 cosine squared of x is equal to 1 minus cosine of x, giving us 2 cosine squared of x plus cosine of x minus 1 is equal to 0. And at that point, that should look very, very familiar, because that is an equation that we solved earlier. And where is it? There it is, right? 2 cosine squared plus cosine minus 1. And there it is, 2 cosine squared plus cosine minus 1. So we in fact already know the solutions to this. X in here is going to give us pi over 3, 5 pi over 3, or pi. Essentially what I'm saying is, after some steps here, this becomes 2 cosine of x minus 1 times cosine of x plus 1 equals 0. So that's how I get these solutions, all right? But the step from the work from here to here, we already did it in the first example, so I'm not redoing it, but we know the solutions here. And notice that in here this time, I kept it within the unit circle, so I didn't add the period to each of these solutions. All right, so that was the half angle formulas, and we did the power reduction formulas. There's other formulas as well, all right? And some of these are called the product to sum formulas. Product to sum. And those would be as follows. Sine of u times sine of v can be written or rewritten as 1/2 times cosine of u minus v minus cosine of u plus v. Similarly, cosine of u times sine of v would be 1/2 times cosine of u minus v plus cosine of u plus v. If I had sine of u times cosine of v, that would be 1/2 times, not cosine, sine of u plus v plus sine of u minus v. And lastly, if I had cosine of u times sine of v, this would be 1/2 times sine of u plus v minus sine of u minus v. All right. Now, as far as where these come from, well, it turns out that these are just very clever ways of manipulating some of the formulas that we already have. I'll go ahead and prove this first one. All right. So here's the proof. Now, cosine of u minus v, let's recall what that was. Cosine is cosine, cosine, sine, sine. So I have cosine of u times cosine of v minus, not minus, plus, right? Because with cosine, the sign changes. Plus sine of u times sine v. And what we're looking for here is sine of u times sine v. Look at that. So we're going to be able to manipulate this somehow. Also recall that cosine of u plus v is equal to cosine of u times cosine of v minus sine of u times sine v. Now, if I were to subtract these two, as hinted of by there, if I were to subtract these two equations, well, on the left side, cosine minus cosine, well, I have cosine of u minus v minus cosine of u plus v. Then cosine u cosine v minus cosine u cosine v, these cancel each other out. Sine u sine v minus a negative sine u sine v, well, minus negative means plus. These are both the same, so I end up with 2 sine u sine v. At that point, well, if I divide both sides by 2, I end up with 1/2 times cosine of u minus v minus cosine of u plus v being equal to sine of u times sine v. And look at that. That's essentially the same as this line over here. I just have it written the other way. All right, but it's just really very clever ways of reusing these. You can prove the other ones in the same exact way. Instead of subtracting these, if I added them, you would end up with this addition on the inside, and you would have that. All right, similarly with the sine of u plus v, if I add them or subtract them, I can somehow rearrange the result to look like this. All right. All right, now how is this, how can something like this be used? Well, if I said, so example G, rewrite as a sum or difference, or. And I can start with something like sine of 5x times cosine of 3x. Right? Sine of 5x times cosine of 3x. Well, I'm going to use this right here because I have sine of u times cosine of v. So sine of 5x times cosine of 3x. Let's see. According to the formula, well, this is going to be just 1/2 times sine of, well, what was it? We were doing sine times cosine, so sine of the sum plus sine of the difference. So sine of the sum, so 5x plus 3x, plus sine of the difference, 5x minus 3x. Which at this point will give us 1/2 times sine of 8x plus sine of 2x, right? 5 plus 3 is 8, and 5 minus 3 is 2. And now we're done. All right, that's as far as we need to go here. All right, so that was the product sum formulas, right? Now we can also use these formulas, instead of going from product to sum, as a sum to product. Right, so sum to product. And this is product. And that would be something like if I had sine of u plus sine v, this can be written as 2 times sine of u plus v over 2 times cosine of u minus v over 2. If I had sine of u minus sine of v, it becomes 2 cosine of u plus v over 2 times sine of u minus v over 2. If I had the sum of cosines, so cosine of u plus cosine of v, this would be 2 cosine of the sum, u plus v over 2, times sine of the difference, u minus v over 2. And, sorry, I messed that up. That should be cosine as well. They should both be cosine here. All right, so 2 cosine of u plus v over 2 times cosine of u minus v over 2. That was for the sum. And for the difference, cosine of u minus cosine of v, that would be negative 2 cosine, excuse me, not cosine, sine. Negative 2 sine of u plus v over 2 times sine of the difference, u minus v over 2. All right. Now, as far as where these come from, well, very simple. They come from these. All right. So I won't prove that one, but or any of these, but I'll let you figure that one out on your own. It's good practice to try to figure out where these come from, but again, the hint is they come from here somehow. All right. Now, let's do an example here. So what if I said, so we're at example, I think we're at H. Find the exact value of sine of 13 pi over 12 plus sine of 7 pi over 12, right? Now in here, we already know a couple of different ways to manipulate things like this, but let's see how we can use these formulas right now that we just found. So I have sine of 13 pi over 12 plus sine of 7 pi over 12. And notice here that I have the sum of sines. So the sum of sines, what was it? 2 sine, sum over 2, cosine, difference over 2. Okay? So it's going to be equal to 2 sine of the sum, so 13 pi over 12 plus 7 pi over 12 over 2, times cosine of the difference, 13 pi over 12 minus 7 pi over 12, and all of that over 2. At that point, well, what does that give us? That gives us 2 sine of 13 over 12 plus 7 over 12. That's 20 over 12. So 25 over 12. And then we have that over 2. And then that times cosine of 13 pi over 12 minus 7 pi over 12. 13 minus 7 is 6. So I have 6 pi over 12. And then all of that over 2. All right. But let's look at this. 20 over 12. Divide the top by 4. We have 5. Divide the bottom by 4. We have 3. So now we have 5/3. But we have that divided by 2. That's going to be 5/3 times 1/2. So it's 5/6. So that was to rewrite this inside, right? So what we have here is 2 times sine of 5 pi over 6. And then over here, if we look at the other one, we had, well, 6 pi over 12. And then all of that divided by 2. 6 pi over 12 is just pi over 2, right? Because 6 over 12 is 1/2. And then that divided by 2 is pi over 4. So what I end up with here is cosine of pi over 4, which gives me now, well, these are actually in the unit circle. So sine of 5 pi over 6, that's 1/2. Cosine of pi over 4 is radical 2 over 2. Excuse me, I didn't want to write that cosine there, because cosine of pi over 4 is radical 2 over 2. And then 2 times 1/2 cancels each other out. So we're left with just simply radical 2 over 2. Let's do another one that would allow us to solve some equations. So example I. Let's say I said solve sine of 4x minus sine of 2x equals 0. All right? Sine of 4x minus sine of 2x. Well, that's in this format. Sine of u minus sine of v. So we're going to get 2 cosine of the sum over 2 times sine of the difference. All right? So this right here can be written as 2 cosine of the sum, so 4x plus 2x over 2, times sine of the difference, 4x minus 2x over 2. At that point, well, 4 plus 2 is 6. 6 divided by 2 is 3. So I end up with 2 cosine of 3x times sine of 4 minus 2 is 2. So I have 2x over 2, meaning just x. And I get that equal to 0. At this point, I've got the product of things equaling to 0. This 2 is not really doing anything, right? Because if I divide everything by 2, I end up with cosine of 3x times sine of x equals 0. So I've got the product of two things equaling 0. So either the first one is equal to 0 or the second one is equal to 0. In the second one, well, this is saying where is sine equal to 0, sine's equal to 0 at 0 and at pi. Actually, let's do this in 2 lines. At 0 and at pi. But notice I didn't say that it needed to be within the unit circle, so I just need to make sure that I add the period to this. So plus 2 pi n plus 2 pi n. As a side note, I will say that these two can technically be combined to just say x is equal to 0 plus pi n. But then that 0 doesn't really do anything, so we can just say x is equal to pi n. Alright? Because in here, this is so essentially the top one is counting all the evens, right? 0, 2, 4, 6, 8. The bottom one is counting all the odds, 1, 3, 5, 7, 9. But combined, I could just count all of them. 1, 2, 3, 4, so on and so forth. All the multiples of pi. Now over here, for cosine of 3x. Well, I'm going to look at that as this question is really saying, where is cosine of theta equal to 0? Well, that theta is going to be, well, at pi over 2, but also at, well, I'll do it here, but also at 3 pi over 2, right? And at that point, I'm going to say, well, the question wasn't really about theta, it was about 3x. So this one's really saying 3x is equal to pi over 2. You know what, let me make more space here. Let's move this over here. And I'll move this over here. All right. Oh, look at this. I forgot something right here. I should be saying plus 2 pi n on these because the period of cosine is 2 pi. All right. So back to this. I end up with 3x instead of theta, right? Because we know the problem was not about theta. 3x is equal to pi over 2 plus 2 pi n, giving me that x is really equal to pi over 6 plus 2 pi n over 3. Whereas on this side, I end up with 3x is equal to 3 pi over 2 plus 2 pi n. Again, divided everything by 3. So 3 pi over 2 divided by 3 just gives me pi over 2 plus 2 pi n over 3. Alright, so I end up with pi over 6 plus 2 pi n over 3 and pi over 2 plus 2 pi n over 3. So those are technically my 4 solutions. 1, 2, 3, 4. Right? In any case, the idea here in this section in general is that there's other identities that we can use to solve things that involve sine, cosine, or any other trigonometric function, right? Whether we were talking about multiple angles being added, or half angles, or the product of sine and cosine, or the sum or difference of them. There's many ways to rewrite these. As far as which ones you really need to know from this section is the first ones that we started with, all right? And I'll remind you what those look like. These double angle ones. Because if you noticed, they all started with this, and all the other properties or the other formulas that I came up with somehow were built from here, or either originally or from something that was built off of this. So these are really the ones you really need to memorize. In fact, it's really just these, right? These top ones, because we know that tangent can be written as sine over cosine. So you don't even need to memorize this one. But I would definitely recommend memorizing these. But we already know where those come from as well, right? From this idea. In any case, that is the end of 5.5.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.